Thank you very much, Hugo, for the introduction and for the invitation to come again to Lisbon. It's a pleasure to be here and to meet friends and colleagues from a long time ago. And so I'm going to talk about these some systems of elliptic PDEs with critical growth. So the motivation goes back to the classical work of Brezis-Nirenberg from 1983. And so the main goal is like to understand. We know that for Brezis-Nirenberg problem, we have some difference between dimension 3 and dimension greater than 4. So I want to understand how it works in the framework of systems. Okay, so Brezis-Nirenberg, they consider this equation here. So we have critical growth here. And the exponent t here is subcritical, linear or superlinear, but subcritical. So we are in a bounded domain, smooth bounded domain. So 2 star is the critical Sobolev exponent. And so in 1983, Brezis-Nirenberg, they found a big difference between the case n equals 3 and n greater or equals to 4. So for the particular case, when the perturbation is linear, when we have this problem here, so for n greater or equals to 4, they proved the existence of solution for every positive solution, for every lambda positive and smaller than the first eigenvalue of the Laplacian. And this is the optimal interval for existence of positive solution for in star-shaped domain. Okay, for lambda less or equals than 0, we know that there is no positive solution, and this comes from if a positive solution has to be lambda has to be below the first eigenvalue, just multiplication by the first eigenfunction. But this works fine for n greater or equals to 4, but for dimension 3, they proved that there exists a small number, lambda star, that depends on the domain omega, such that no positive solution exists in case lambda is positive and small. So this is the difference between dimension greater than 4 and dimension 3. And this dimension is called, named as the critical dimension for this critical growth problem. So then I want to consider the version of this problem in the framework of Hamiltonian elliptic systems. So the so-called critical hyperbola correspond to the notion of critical growth for Hamiltonian elliptic system. If you just consider the case of with lambda equals 0 and mu equals 0, then the system here will be named as critical if the powers p and q satisfies this equation here. So this is the critical hyperbola. So in 1998, Hulshoff, Mitidieri, and others, they considered the version of the linear perturbation of the Brezis-Nirenberg problem in the framework of Hamiltonian systems. So they investigated this system here. Okay, and then they considered the case with n greater or equals to 4. So in particular, the critical dimension was not treated here. Okay, the critical dimension for the Brezis-Nirenberg equation. So for the critical system, n equals 3 was not addressed in this paper here. And okay, so this is, I'm sorry, this is written in Portuguese. Okay, this is, so this in blue, we have the critical hyperbola. So the homogeneous Lanier system is supercritical in this region here, and subcritical if PQ lies on this part, and on the blue line, it's critical. So this is how we classify Hamiltonian systems. So some interesting results were proved by Van der Vost, Mitidieri, and others. But three problems were left open. So as I said, what does happen in dimension n equals to 3? What's the meaning of critical dimension for Hamiltonian systems? And the investigation of the general one-homogeneous perturbation of the critical Lanier system. Namely, I'm going to present in the next slide a system that I called Hamiltonian system, where I would say that the natural one homogeneous perturbation corresponds to, in the case that R times S equals to 1, which includes the case, of course, the particular case with R equals S equals to 1, that was addressed in the paper by Mitidieri and in Van der Vost. Regarding this question here, what's the meaning of critical dimension for Hamiltonian systems? Is the reason that for second order elliptic equations, n equals 3 is the critical dimension. If you consider the biharmonic equation, then the critical dimensions are 5, 6, and 7. And the biharmonic equation is a particular case of Hamiltonian system. And so this is very natural to try to understand which is the correspondence for the meaning for critical dimensions for Hamiltonian systems. Okay, and okay, this is I already said about the one homogeneous perturbation. So my talk will be mainly focused on a recent work in collaboration with Ângelo Guimarães, where we address the three open problems mentioned before. So for that, we consider this Hamiltonian system here. Here, so this is P and Q. The pair P and Q is on the critical hyperbola. So we have a critical growth system. R is going to be smaller than P. S is going to be smaller than Q. And the product R times S is greater or equals to 1. So R times S equals to 1 is the one homogeneous perturbation. And R times S bigger than 1 is a superlinear perturbation, but subcritical. So it's I would say that this is a lower order perturbation of the critical system in the for either one homogeneous or superlinear. So this corresponds to the first equation that I mentioned to you in the Brezis-Nirenberg problem. As I said, so this is a lower order perturbation of the critical Lanier system, as well as the Brezis-Nirenberg equation is a lower order perturbation of the Lanier critical equation, this equation here. And the condition 1.4 on the pair RS correspond to T equals to 1 or larger than 1 and subcritical in the Brezis-Nirenberg equation. And this is the main theorem that we proved. So let lambda and mu be positive. Assume that the pair RS is subcritical or one homogeneous. Well, one homogeneous or superlinear and subcritical. And in the case of one homogeneous perturbation, we also suppose that this product, lambda times mu to the power r, is suitably small. If the dimension is 3 and p is less or equal to 7/2, or p is greater than 8, so this is in the case of dimension 3, or if we are in dimension greater or equals to 4, then we prove the existence of a positive solution. So regarding this condition here on the parameter, let me just go back to the system. So observe that this is, I have here the lambda and mu appears here in the perturbation. Okay. When I say that lambda times mu to the power r is small, this is very linked to a recent work with Hugo Tavares and Delia and Gabriele, where if you see that when lambda times mu to the power r is a constant, this is the so-called critical, the first eigenvalue curve. So when I say that this is more or less, indeed, it corresponds to say that we are below the first principal eigenvalue curve. And this is again as in the Brezis-Nirenberg problem. If you see in the Brezis-Nirenberg problem, they assume that for this equation in the one homogeneous, in the linear perturbation, so the condition is lambda is below the first eigenvalue. Okay, and this is the precise the assumption that corresponds to this assumption here for the second order equation. And okay, so I want to say something about this result before going to details. So I'll show you the precise condition of the size of this product here in the case of r times s equals to 1. And as I said, it corresponds to this condition here for the Brezis-Nirenberg problem. And regarding the case n equals 3, we must notice that the pairs 7/2, 8 and 8, 7/2 are symmetric points on the critical hyperbola. And so particular case of the systems. In case the parameter lambda equals to mu, the powers r and s are equal, p and q are equal, the system reduces to the equation of Brezis-Nirenberg, okay? In the sense that every solution has to be such that u equals v. Okay, so in this particular case, we reduce the problem to the Brezis-Nirenberg equation. For n equals 3, the critical dimension for the Brezis-Nirenberg problem, and this is the one of the, I would say, the interesting contribution in the paper. We prove existence for P and Q in some parts of the critical hyperbola, even if in the case with R equals S equals 1, that was treated in the paper by Mitidieri and van der Vost, but they consider the dimension bigger than 4. So comparing to the paper of Mitidieri, van der Vost, which are the contribution is threefold. We treat the case of dimension 3, as I said. For n equals to 4, due to some technical condition. So in this paper 8 here, Hurchov, Mitidieri, and van der Vost, they consider P different from 2 and P different from 5. It's what was technical. This is very delicate estimates, and they could not manage to get good estimates for this case. So if you see in dimension 4, and if you look at the hyperbola, they removed 2 points in the critical hyperbola that they could not treat. And for n greater or equals to 3, we consider one homogeneous perturbation or superlinear perturbation. And in the paper 8, they were restricted to the case with R equals S equals to 1, and then both P and Q are superlinear. And here we treat all points in dimension greater or equals to 4. We treat all points on the critical hyperbola. In dimension 3, we have some restriction, but this is again linked, and this is what established the link with critical dimension.
You see that R is smaller than P, and S smaller than Q.
Yes.
So it's not any.
But yeah, but so this is a good remark. But yeah, but we perturb. This is lower order with respect to this, and this is lower order with respect to this. Because if this is already critical, if this is okay, if this is subcritical, but this is greater than this, we are not in the good space for doing the variational treatment. This is a good question. That one should remove this, but I don't know if it's possible. This is a good question. And okay, just a second. Okay, so this picture gives the idea what are the results that we get. So this is the critical hyperbola for dimension 4. For dimension 4, we have this is asymptote here, because the asymptote is 2 over n minus 2. So in dimension 4, this is 1. So we take any Pu on the critical hyperbola, and any pair RS, which is lower order perturbation, lower order with respect to PQ, and one homogeneous when we are on this line here, or superlinear. So for every pair RS, we manage to get a solution. This is the critical hyperbola for dimension greater or equals to 5. So we know that this asymptote here is less than 1. So we managed to take, so every, we consider any point on the critical hyperbola, which includes cases where P or Q is less than 1. And our result says that for every RS on this green region here, including this line, we prove the existence of a solution. So we had some extra assumption in the case of dimension 3. And this I am going to establish a link with the paper of Brezis-Nirenberg. So for dimension 3, it's not possible to prove existence of positive solution for the Brezis-Nirenberg equation in the full interval. So I'm going to put here. So this is the Brezis-Nirenberg equation. So we cannot prove the existence of solution for every p t less than 5 and greater or equals to 1. And indeed, as proved in Brezis-Nirenberg, and also in the Brezis-Lib paper. This is a paper of Brezis-Lib from 1985, where they proved some, they call Sobolev embeddings with some reminders. And what they do is that the existence of solution holds only for t greater than 3 and less than 5. And this leads to the following definition for system. For n equals to 3, let PQ be a point on the critical hyperbola, and omega is a bounded regular domain. And RS subcritical in lower order perturbation, and one homogeneous or superlinear. So this is the condition on point 4. We say that the point, the pair PQ is on a critical region of the critical hyperbola if for some omega and some RS, HS does not have solution for lambda and mi is small. This is again here, because in case dimension, so this for dimension 3, there is no solution if T is less or equal than 3 and lambda is small. So for lambda is small and T greater than 1 less or equal than 3, there is no solution for the Brezis-Nirenberg problem. So this means, and this, which let's say that this is the critical dimension. So this is this corresponds to that notion there. On the other hand, PQ is on a non-critical region of the critical hyperbola if for all omega and every pair RS lower order perturbation, one homogeneous or superlinear, and lambda and mu is small, suitably small is going to be, this is again for, we know that for lambda large there is no solution in the linear case, for example, okay? So the system has a positive solution. So let me establish some connection with critical dimension for the biharmonic operator. In this paper from 1994, and also I would mention the paper by Gazola and Gruneau from 2001, and Gazola and Dvet from 2010. And originally, it was okay in this paper from Van der Vost. He proved that the dimension 5, 6, and 7 are the critical dimensions for the biharmonic equation, for this biharmonic equation. And this is a particular case of the Hamiltonian system. If you take the Hamiltonian system with lambda equals 0 and p equals 1, we have this here. So here we have the 3 dimensions that are critical. And then some time ago, with Jessica Lange, we start investigating this phenomena of critical dimension for Hamiltonian systems. So the first attempt, I would say, that was in this paper with Jessica here from 2015. However, in this paper, what we did, we consider particular case of perturbation. So we consider minus Laplacian of U equals to the V to the Q minus 1 V, and minus Laplacian of V equals to lambda U to the Q. What I'm going to put here? R minus 1 U plus U to the power P minus 1 U. And so here we did the perturbation was just in this spot. So this was an asymmetric perturbation. And in this case, for this particular case of perturbation, I would say that the system is more like a biharmonic equation. Because we did this because we used the reduction by inversion, and we consider a fourth-order equation, which is more or less a P. If you look at the P Laplacian and compare to the Laplacian version, so this would be the link between this P biharmonic problem type. This is going to be a type of P biharmonic problem. But I would say that this is not natural perturbation for the system because it's asymmetric. So this is, and indeed this is, in some sense you could say that this is weak. Because when we also put this I would say, the mu part here, what we're dealing now is we have mu to U to the S minus 1 U. Okay, so these are stronger perturbation, stronger than if we do not have this part.
Show the system again. Your system.
Okay, hey, is that one?
Wait, is there the perturbation is in U or?
I'm sorry. This is V.
Okay.
Okay, thank you. This is V. Okay, so this is a kind of symmetric perturbation. And so in this paper with Jessica, we consider asymmetric perturbation, and this makes the problem more like a nonlinear version of the biharmonic, as I said, as the counterpart of the P Laplacian version for the Brezis-Nirenberg problem. In the case with lambda positive and mu positive, precisely the system that we consider here in this paper, this is which the natural symmetric perturbation, we recover that the only critical dimension is n equals 3. Because when we consider this version, which very looks like the biharmonic, for the biharmonic, we have 3 critical dimensions, 5, 6, and 7. For this case, we also had some a range of which would be critical dimension. But indeed, again, we could read in the sense of parts of the critical hyperbola. But we are not happy. But I would say that for the natural perturbation, this one that I'm talking today, well, so we recover that n equals 3 is the only critical dimension, but as it happens for the scalar problem, but we unveil the notion of critical and non-critical regions of the critical hyperbola. So how do you proceed? So the argument is for people that have worked on this kind of critical equation, we know that we have to make very delicate estimates. So this is the variational treatment. We here write the system as a 4th-order equation. We take the system. These, what I do here, F lambda. So, okay. You see, this is what I call F lambda of U. So this is F lambda is this function here, which is strictly increasing. So it has the inverse. So I take the inverse here, and then I have that the inverse of minus Laplacian of V equals to U. And then I plug this here. I plug this here, and then I rewrite the system as this equation here. Okay. Of course, I could also invert with respect to the other equation, and I have the second equation here. So this is it's equivalent to solve the system. Okay, this is one of the variational treatments for this kind of problem. What's the problem here? What's make the problem a bit complicated? Is that this the function f lambda is not homogeneous, so we have different powers here. So this makes the estimates a bit more delicate. So we search for solution of this fourth order equation here. And in the variational treatment, weak solutions correspond to the critical points of this function out here. Okay, where f lambda bar is the primitive of the inverse of f lambda. And then we investigate, we search for critical points of this functional here.
The regularity of the f lambda is what?
Yeah, R can be smaller than 1. It's continuous, but it's at 0, it's going to be Hilde. When R is less than 1, it's not Lipschitz. Okay, so this is, yeah. So, but we also consider this case there. So what we do? So we make so it's not difficult to see. So okay, we search for critical points of this functional in this space here, P, where ET is this Sobolev space, this second order Sobolev space here. And we consider this node here in this space. If we invert with respect to the first equation, then we treat the problem using this functional here. Okay. As I said, this approach is usually named as a reduction by inversion. It was used a long time ago by Pierre-Louis Lyons. And as I said, some extra difficulties comes because F lambda and G mu are not pure power. And then we have to do some delicate estimate to capture, because when we invert, we keep this part here, but then we have the non-homogeneous part in the first equation that comes from these. And so we have to capture in these, in the fourth order part, the contribution of lambda, of this part here. So we do some asymptotic analysis, either when U is closer near 0 and also at infinity. And what we show that in order to prove, so we have to capture this contribution to downsize the mountain pass level, to downsize to a region where we have compactness. And so what is some maybe new in the arguments, but not simple to understand, because this is in order to see when we get this contribution. If you look at original problem of Brezis-Nirenberg, when doing the estimates, he has to multiply the ground state by a cutoff function, and then to analyze the decay of the ground state. So more or less, they integrate on inside balls or outside balls. In order to capture this contribution, we also have to make some estimate on the rings. And so this is somehow just technical part, but this is what's different. And then the standard, since we are in the superlinear regime perturbation or linear, but below somehow the principal eigenvalue curve, so we have the mountain pass geometry. Okay, and as I said, for the particular case of one homogeneous perturbation, we ask, this is the condition that we ask, this product here. Observe that since r times s equals to 1, this and these are equivalent. Here, if we put the power r here, so I would say mu to the power r, but r is 1 over s. It's what appears here. So this is more or less equivalent. And see, and this number here is correspond to of the embedding of the space EP in this Lebesgue space here. And this, for in particular, for those that are working on the eigenvalue, principal eigenvalue curves, I would say that this is more or less that we are below the first eigenvalue curve. Yeah, in our paper, the eigenvalue, the main eigenvalue curve is when this is equals to a constant. So this is, we parameterize the eigenvalue curve. And as I said, this condition, so the both of this condition here, this is to treat when we use this inversion here, and this is to treat in the case that we use the inversion of the first line. This corresponds to the case lambda less than lambda 1 in the Brezis-Nirenberg problem, or in the Mitidieri, Ulshoff, and van der Vorst, when r equals s equals to 1, when they ask that lambda times mu, since r equals to 1, is precisely when r equals to 1, so lambda times mu is small. And this is not only technical, it's sufficient, but it's also necessary. When we are above the first eigenvalue curve, you have no positive solution. Okay. Okay, so this is the spectral curve. Okay, and so as I said, we use to get solution is very standard. We have the mountain pass geometry. I mean, under the hypothesis, we have the mountain pass geometry of the both functions. So, but the problem is critical. We have no compactness everywhere. So we localize the range of values where we have compactness, and then we must show, as is standard at Brezis 30 years ago, 40 years ago, to show that the mountain pass level is in the region where we have compactness. So this is very standard, not new arguments, but very delicate estimates. And then we localize, you see, we have to localize the levels where we have the PSC condition. So this is here, as in Brezis-Nirenberg. And then we show that the mountain pass level has to be in the where we have compactness, and there where the restrictions on P and Q enters. And that is where motivates to define the critical and non-critical regions of the critical hyperbola in dimension 3. In dimension 4, there is no restriction. As I said, if n equals 4. This, of course, I can always, the hyperbola is symmetric. So this is P is less or equal than this number, or Q is less or equal than this number. So it's not a restriction because one of the powers satisfies this. So suppose that we are in this part of the hyperbola. So for n greater or equals to 4, no restriction on P, or if n equals 3 and P is less than 7/2, then the mountain pass level of the function is on the good range, is on the range where we have compactness. So this is the argument. I'm not going to enter into details. I'm running out of time. So I have some open problems on ongoing work. Maybe this is a good picture to show you. So as I said, in dimension 3 is where we have critical and non-critical regions. So in this blue part, we can get solution. If P and Q is in the blue part, we are in the non-critical regions. We have solutions. When P equals Q, R equals S, lambda equals mu, we are in the Brezis-Nirenberg setting. And so we know that there is no solution for the linear perturbation, okay? So this is a point, a part on the critical region, but we have some restriction. We are only able to treat this region and this region, and we conjecture that all these gray parts must also be red. So must be critical. Okay, so this is one of the, we should have to classify, and everything here, okay, there is a recent paper by Kim and Pistoia regarding this kind of systems, critical system, but in the case with R equals S equals to 1, and they investigated, so the problem is critical, they have this linear perturbation in both equations, and they investigate the blow up when lambda equals mu goes to 0. So it would be very natural to consider the same kind of problem, but with R times S equals to 1. So this is could be something to be done because it's very natural. And something that is very linked and also works to show the non-existence for solution in the critical dimension is the so-called Sobolev inequalities with remainder terms. We know that here is, for every dimension, we know this comes from the Sobolev embedding. But Brezis-Nirenberg, they showed that, okay, I can add a little bit more. So this is the weak LP space, with P being half of the critical power. So they proved this equation. And this, if you look at this equation, we get Y. We just use the Nehari manifold or the Nehari identity combined with this, and you see that there is no, since this is positive, okay, we use that this is embedded in L2, okay, and then what we see very easily, standard calculations, that n equals 3, you have no solution for the Brezis-Nirenberg problem with t equals to 1 for lambda small. And Gazzola and Vet in 2010, they proved this problem, the version for this for higher order problem, but in the Hilbert scenario. Okay, and for the problem here, you see that we work on this kind of space. Okay, so this would be very natural to get these Sobolev inequalities with remainder for this spacing. And then this would help to prove that no solution exists and to classify to get more accurate answer to the critical regions. Okay, so these are the paper. Just to show that, let me name correctly the authors of the main paper. I'm sorry, I know this is the paper. So it was, okay, I was correct. Hulshoff, Mitidieri, and Vanderpost. So this is the main reference linked to the paper when they consider the Hamiltonian system, but for linear perturbation in both equations. Okay, I'll stop here. Thank you very much for your attention.